presentation is CAREM design and construction experience. I will start telling you what is CAREM. Maybe most of you don't know. CAREM project consists of the development, design, and construction of small nuclear power plants based on integrated pressurized water reactors. This is a project that is important to Argentina to sustain activities nuclear power plants designs and construction area, assuring the availability of updated technology in the midterm. Argentina has experience in running and operating nuclear power plants, but these nuclear power plants are heavy water natural uranium plants. And we also have experience in construction and design of experimental reactors. The last plant that Argentina finished was Atucha 2. It was a German design from many years ago, but it was stopped during the 90s. And less than 10 years ago, it was finished by Argentinian people because German people went out of the business. But we are very proud we were able to finish, and the plant is working properly. So I told you that Argentina has also experience in research reactors. These are reactors for experiment and also for isotope production. We have had many of these reactors built around the world. We have built reactors in Argentina, Peru, Algeria, Egypt, Australia, and we are finishing one in the Kingdom of Saudi Arabia. We have also self-engineering, for instance, the engineering in Brazil, with one, and we are doing the conceptual engineering for a research reactor that is planned in Netherlands to produce radioisotopes. So the aim is to export SMRs, like we have succeeded with experimental reactors, in a market that we know it could be very competitive. So the first step is to build a prototype. Well, really, for the first step was to develop a lot of technologies and research. But our step now is to build a prototype. This will provide the design basis for a commercial power plant, will facilitate the licensing process of a commercial CAREM. This will develop abilities within our organization and the country and the companies in the country related to supplies for nuclear power plants. And this will facilitate the export of nuclear power plants in a competitive market. The construction permits were obtained and the construction is ongoing in Atucha site. So this is close to the nuclear power plant I have told you we have started less than 10 years ago. The name of the prototype is CAREM 25. The main features are an integrated primary cooling system. The primary cooling is by natural circulation, and the reactor is self-pressurized. These are not unique to CAREM, but the combination of these three characteristics is, I think, unique to CAREM. So I will explain a bit what this means, because when we were preparing our licensing process, we have a consultancy, we have hired people from Netherlands that have experience in thermohydraulic stability. And after reviewing, they told us, what you're doing is okay, but try to explain to people the differences with conventional reactors because it's important, because they will not understand you if you don't properly explain it. Something like what Sean has said about the regulatory bodies. They need to be explained what you are doing. And of course, our regulatory body asks the same. So I will take a bit about these differences, and if you know a conventional PWR, you will recognize some differences. And then I will summarize the construction status of the protocol. Well, let's talk about integral pressure water reactors. In order to simplify the design, the whole high energy primary system, the core, the steam generators, the pressurizers, the pumps, are contained inside a single pressure vessel, not connected by lines like in a conventional PWR, a loop type conventional. This considerably reduces the number of pressure vessels and simplifies the layout, but of course, the pressure vessel is bigger. Due to the absence of large diameter piping associated with the primary system, no large loss of coolant accident has to be handled by the SSD system. This really, the elimination of large loss of coolant accidents considerably reduced the emergency core cooling system components and also AC supply systems. The large coolant inventory in the primary system results in a large thermal inertia and a long response time in case of transients. We also have self-pressurization and natural circulation. Natural circulation means that we eliminate the primary pumps. We also eliminate the pressurizer. After we eliminate the primary pumps, we don't have to live with the loss of flow accident, or the loss of flow condition. And there are also advantages for maintenance and availability. The self-pressurization of the primary system, we have a steam dome on the top of the pressure vessel. The self-pressurization is a result of liquid-vapor equilibrium in this dome. The large volume of the integral pressurizer also contributes to the damping of eventual pressure perturbation. Heaters and sprinklers, typical of conventional PWRs, are eliminated. They are not used to control the pressure. The flow rate in the primary system is achieved by natural circulation. The driving forces obtained by the difference in the density along the circuit are balanced by the friction and form losses. Produces an adequate flow rate in the core in order to have sufficient thermal margin to critical phenomena. We can see the red region is hot water with lower density, and the blue region is cold water with higher density. So that's produced the buoyancy needs to drive flow. Reactor coolant natural compression is produced by the location of the steam generators above the core. This is not different from what's happening in a conventional PWR. In a conventional PWR, you also have the steam generators above the core, not to handle the normal operation, but to remove the residual heat by natural circulation. So we will make a few balances, but don't worry, it will be not hard mathematics. Let's consider the dome, where we have the vapor and the liquid interface. There are condensations in the dome. If we have a certain amount of power that we condense in the dome, we need to have a vapor flow from the reactor to compensate the vapor that is condensed in the dome. And we can get a thermal balance, and we can see, depending the amount of condensation we have and the flow rate in the primary system, which will be the quality at the exit of the riser, of the chimney. This title will bring the vapor we need to replace the condensed vapor in the dome. We can also make a thermal balance along the riser, chimney, and the core. We can consider that the chimney is adiabatic, so it's very simple. But in the core, making a thermal balance, we see that the difference between the inlet and outlet quality is related to the flow rate and the power that is produced in the core. And then we can get the inlet quality that is the quality we have at the inlet of the core. We can see that if we are operating at a higher power, this means this value is higher. Also, the condensation is very low compared with the power we produce in the core. This number is negligible. If we increase the operating power at a given stationary state, we see that the quality will be more negative. This means that we are operating at a higher power in a stationary state. We will have a colder flow going into the core. What usually happens in a PWR? If we increase the power, the inlet temperature to the core is higher or lower? Let's consider a conventional PWR with two-tube steam generator. You know what? If we increase the power, the temperature is higher. The reason is the steam generator, the tube steam generator, is a heat exchanger with a constant area. And if we increase the power, we need to increase the temperature difference between the primary system and the secondary system. The secondary system temperature is related to the saturation pressure. In PWRs, you usually do different things, but you can increase a bit the pressure of the secondary side to increase a bit the power, but you cannot increase too much. So finally, if you reduce the power, you have to reduce the temperature of the primary system to balance the system. Well, in our case, it's the opposite. How can we handle it? We handle it because our steam generator, there are of one through type. One through type is a steam generator that do not produce saturated vapor, but superheated vapor. So we balance the system, increasing the superheat when we rise the power, increasing the temperature of the superheated vapor at the outlet of the secondary system. Let's talk a bit about the natural circulation. In CAREM reactor, the quality is very low. We need very small quality to refill the vapor. So we can consider a single phase flow with a reasonable function. And if you make a simple equation, consider a single phase natural circulation, reducing approximation, and if heat flux is uniform, you will get a well-known result, that is that the flow rate is related to the nuclear power, but not in a linear way, with the cubic root of the nuclear power. So if you increase the power, you slightly increase the flow rate, but not in a linear way. This is a classical shape. These are the real results compared with this single equation, and this is a very good approximation for a wide range. Here I am giving you some reference. If anyone wants to read more, you can. This is in the open literature, and you can find it. I have told you that the inlet temperature is lower. I will now demonstrate you that. If you make an energy balance, you will find that the difference between the inlet and the outlet of the core enthalpy is related to the power generated divided to the flow rate. And this is the result using previous equations. You can calculate not only the inlet temperature. You can calculate the average temperature or the average enthalpy of the primary system. This is the traditional variable used by PWRs to control not the inlet temperature, but the average temperature. That is related to an average between the inlet and the outlet temperature of the core. And you replace in previous equations, you can get the result. Remember that this is very small, so if we increase the nuclear power, we see that this term is bigger, but have a minus sign, so the inlet enthalpy is reduced. Okay, this is the same result applied to the inlet temperature and this. So one thing what we can see is the inlet temperature is not something that you control. It's related to the balance associated with the power you are generating, the condensing power you have in the dome, and the pressure you have in the system. Here is a graph just to see what we have seen in the equations. In green, we see the difference between the outlet and inlet enthalpy. When you increase the powers, you increase the difference of temperatures between the inlet and the exit of the core. And when you increase the power, the inlet enthalpy, the inlet temperatures, goes down. Why do you think it goes down? Physically, very easy. You have a steam dome, and we have to provide very little vapor to compensate the condensation. So, which is the temperature at the outlet of the core? Higher. It's saturation temperature. So, you can consider that at the outlet of the core, you are close to saturation temperature. In a PWR, you don't have that. The outlet temperatures depends on the power. That is the difference, and this is related to the self-pressurization. Yep. Why is this important? Because you need to understand that the natural behavior, the different states you will get, are simple, but not just the same as in a conventional PWR to understand the whole Reynolds machine. The feedbacks you will have. And this is important because one thing we have to analyze is the primary system stability. Anyone knows about what is a density wave stability? Density wave stability. I will tell you. This is many PWRs have had this problem. Also, many PWRs, but in the steam generators. When I was younger, in the 90s, in a Tucha 1 nuclear power plant, not the one we have finished, the older one, the steam generator has oscillated, and I have to go there to do something. And I can see in the control room the pressure oscillating in the steam generator. The pressure oscillates because the flow rate inside the steam generator was oscillating. So one of the things you traditionally do is to analyze the stability to avoid this kind of problem. As in CAREM we have a little vapor, little quality in the riser, we have to check the stability. Single phase system would also have instabilities, but it's not so often. So, type 1 stability mechanism is dominant in current reactor since it operates at low quality flows. Under these conditions, the mass percentage of steam at the core outlet becomes very small. For small quantities, a particular low pressures, the volumetric amount of steam increased very rapidly as a function of the flow quality. A small decrease in the flow then leads to a large increase of the volume of steam produced at the core outlet. In a natural circulation reactor, this causes a low density wave traveling through the chimney. If we change the quality, we change the amount of vapor, so we change the density. And this goes with the flow. That's why they used to call density waves. It's a natural circulation, so the flow is driven by difference of density, so it's all related. This enhances the driving head and the inner flow will increase. Then the opposite process occurs and the void fraction in the chimney decreases. Consequently, the driving head becomes smaller and the flow rate will decrease. This completes one cycle of a type 1 oscillation. If you have stability or not depends on the feedbacks. If you have the proper feedbacks, it will be stable, but if are not proper, you can have an oscillation, like in many control systems. One thing that is important in CAREM is the flashing phenomenon. Everyone knows what is flashing. We will call flashing when we have vaporization, but not because we are heating, just because the pressure change. And we are very close to saturation, and when we are going up to the riser, the pressure is slowly decreasing because we don't have water inside. Oh. So this small decrease produces a little vaporization, and this is what we call flashing. Of course, this production of vapor in the riser directly affects the gravitational pressure drop over this section. We can calculate lambda. Lambda is the distance from the top of the chimney to the point where the flashing starts. And if we replace with previous equations, we can get these results. As the flashing changed the density of the chimney, this has an important effect, or could have an important effect in density wave stabilities, because it changes the density along the riser. This is a picture to show how the position of the flashing point changed with the core power. It's not depending on the power, the position where you need to start flashing is different. You can see that for high powers, you start flashing in the chimney, but for low powers, you need to start flashing inside the core. But we can discuss if it is flashing or not. Okay. In order to have a constant pressure during normal operation, some vapor needs to be created in the reactor pressure vessel. Besides some vapor created in the core, this amount of vapor is created also by flashing in the chimney. Assuming that the coolant is saturated at the exit of the core, just traveling through the riser and changing the pressure produce a vaporization that is similar to about half a megawatt. This is a value for the protocol. Of course, change the reactor size. The presence of this vapor produces necessary self-pressurization. Such amount of vapor is separated in regions located over the chimney and condensed in the dome in the surface of the control mechanism? Well, in the dome, there are different things, but you can condensate. Some vapor will be condensed. So you need to replace it and just reduce all these effects. But what is important is in the upper part, the area is very big, the flow are low, so the bubbles produced in the riser goes to the dome and they don't go down through the steam generators back to the core. And so it's a gravitational separator. Let us assume that the vapor generation rate is larger than the condensation rate. So we are producing more vapor in the core than what we are condensing in the dome. Under such condition, the system pressure will increase because we are increasing the volume. And the fletching effect will diminish. So we will stop the production of new vapor. So this will maintain the pressure constant. Here is just to show that if you have different amount of vapor condensed at the dome, the position of the flashing point change. This is the case where we have a very high condensation in the dome, and this is a case where we have a much lower condensation. So depending, this is the top of the riser, and this is the bottom of the riser. So where we need to start the flashes depends on the power and on the amount of condensation we have in the dome. If we change the condensation of the dome, different condensation in the dome, change the flashing point. One thing that was important was to identify the natural variables of the system. Well, if you study instabilities, you will have many well-known numbers, but we need to relate these numbers to our own system. So something that is important is the pressure, because the properties and the saturation temperatures depends on the pressure. The nuclear power, we see that all these things change if we change the nuclear core power, and also the condensation in the dome. If we change the amount of vapor that we condense, all the things change. So these are the three main variables to be taken into account. If someone knows something about density wave instabilities, there are many numbers like the phase change number and the subcooling numbers that they are traditional to analyze this kind of phenomena. So one of the things we have to do is relate these numbers with the core power and the condensation power, and to change the way we make the graphs. So what in the conventional numbers looks like this, in our variables looks like this. So if someone knows this kind of graph, using our variables, this graph will look like this. Well, to analyze these instabilities, one of the things you need to do is to compute them. But you can't use conventional codes to analyze stability. Conventional codes use some numerical diffusion to stabilize the behavior and to facilitate the solution. But doing that, you do not represent instability behaviors. So one of the things we have to do is to develop a specific code to analyze the stability behavior. In the specific code, one of the things you try to do is to avoid or reduce as much as you can numerical diffusion. And if you know something about numerical methods, you will see that in this kind of system, one thing that is important is the current number to try to avoid diffusion inside the cell. So you need to make special nodalization to take into account that the Courant number goes to the limit to reduce numerical diffusion in the. So there are a lot of things you need to do, but this is an important concept because you cannot apply the conventional code to every problem. They are well and they work well when you assume that you don't have stabilities, but they are not good to find the stabilities. Okay? So, after working a lot, we can get the stability maps to see where you can get stable regions and where you can get unstable regions. Well, all the blue thing region is stable. And we found a very narrow and stable region at low condensing powers. This is a zoom of this region just to increase that. So this region, if the condensing power is about this, the system is a bit unstable. We can, you remember which was the power supposed to have saturation at the exit of the core, I have mentioned before. If we consider we have saturation at the exit of the core, that means that we have evaporization similar to 0.5 megawatts. So, the more stable situation is when you start to produce, the flashing point is close to the beginning of the horizon. If you have up in the horizon or inside the core, the system is very stable. To explain that, you need to, it's longer, man, believe me. If you have it inside the core, changes in density are very low, and if you have the flashing point up in the chimney, density changes are larger, but in a narrow region, so the whole weight is less and the influence is small. So, one of the things we have done is, okay, how big are these simulations? Okay, to model this, of course, again, to look at the Coulomb number and to model that is very important. What we have found is that due to nonlinear effects, the amplitude of the oscillation is very small. Very small. The flow rate really changed very low, very small, very little. Why? Because the difference, the motion force we have is very low. So we don't have much driving force to get very large oscillation. But anyway, we'll try to avoid it. So, one of the things we have found is that the flashing phenomenon is important. The pressure feedback is stabilizing. The core dynamics also is stabilizing. If you get the flashing inside the core, the nuclear feedback stabilizes the system because they control the nuclear power produced. There are nonlinear sources. What is nonlinear sources? This, for instance, if you have a very high flow, you can get all water. You have no vapor production. And this is something that is changed the linear behavior. Also, you can have, due to the enthalpy waves, you can have more than one flashing point in the horizon with the proper frequency. So there are different things that we have. But even the idea is to avoid. So it seems that they will have a very little amplitude, but we will avoid. most important, the condensation taking place in the steam dome has a great impact, defining the stability of the reactor. So, what we have done, we have introduced a coil in the dome to set a constant condensation rate that is all inside the stable region. We are not controlling the condensation. You know that a reactor has a chemical and volume control system. This system takes water from the reactor, cool it, and then purify it and go back to the reactor. So a part of this water is sent through a coil to the steam dome, and this produces a condensation that assures that the system is in the stable region. We have also made a high pressure, high temperature loop to prove the behavior. This loop is full height, not the other dimensions, and working at the nominal pressure of the reactor. And we have made many experiments to get data to assess the code we use to represent the reactor. And here I will say something. In the test loop, we never found instability. Why? Even the height is the same. As the size is smaller, the external surface is bigger compared to the volume than in the reactor. So the losses, thermal losses and condensation is a bit higher than in the reactor. So the system was always in the loop, in the stable region we have seen where we have a higher condensation. So the whole phenomena and the whole things is consistent, and what we are sure, if we can ensure that the condensation have a minimum value, the system is stable. Any question?
It's about neutronics.
When we make the model, we include neutronics. And the neutronics was part of, when you get vapor in the core, neutronics helps us to stabilize the system, because the feedback is very fast. Usually, if you have a fast feedback, this stabilizes the system. The problem is when things that take time to change.
Also about the control rods, if your vapor, let's say, the height at which your vapor starts is changing, you need to calibrate your control rods because their efficiency is also changing to some extent. Like
remember that the quality is very low. So the effect on the weight of the rod is not in the WR. It's very, very small fraction. You can consider it almost single phase. Well, let's talk now a bit about the construction. We have finished with these things that are unique but very important to explain what we have and to be properly analyzed and by the regulatory body. So I will do this very fast. Here we can see some picture of the site. This is the containment. This is the reactor building, the turbine buildings, and other. The progress is about 70%. Atucha plants are in this area. This is the containment liner. It is important because, well, it's like a building, but it's a steel construction that you need a special engineer to do that. And here I can say, the people who designed this was a German company. So we have paid a German company to make the engineering of the line. We're building it, but we have contacted a German company to make the engineering. It's not so easy to design a liner. It's a mechanical design, but a liner is something that wants to avoid leakage, but must, if it is so very hard, can make pressure, can make stress to the concrete, so it's a balance. So the design is different like a pressure vessel. It's not a pressure vessel. The progress is about 90%. There are some points to finish, but the containment is almost, the liner is very close to be finished. The balance of plant is related to the part that is not nuclear, what we need to produce the vapor and the electricity. This is about 63%, a bit more. We have some new things, but not far for that number. Again, the turbine and the generator, in our case, is German. So we still buy things to do the reactors from Germany. The pressure vessel. Well, in our case, it's something important because it's the first time we are building an end-stamp pressure vessel in Argentina. So this is a local company that is producing it, but forges are Italian. So the forges are producing it. All the construction, welding, machining, all is done in Argentina. The end stamp is Argentina, but the certified forges are Italian. Okay, the progress is about 65%. Steam generator is also something that is no new. This kind of designs are Russians, but we are making our own development. As Sean said, it was a long way to develop the construction techniques. And also, we have to build a special oven to make the treatment heat because our tubes are a bit longer than conventional U-tube steam generators. So we have to build our own oven to make the treatment because they're a bit longer than they have 35 meters. That is a bit more than what conventional U-tube steam generator have. So the tubes are already produced, and now we have the contract to build the first complete steam generator that will be tested, but also making extractive tests. We will break it to see that it complies with all the requirements. Okay, well, the fuel assemblies we produce also in Argentina. The company that produced the fuel assembly is the same company that is building the liner. There is a company that belongs to the Atomic Energy Commission. It's a joint venture between the Atomic Energy Commission and a private company. And it's the company that produced fuel elements in Argentina for the other nuclear power plants, Atucha 1, Atucha 2, and Empalme. Okay, thank you.
Thank you. Very impressive. When you see the nuclear reactor under construction, is always very good news. Question, please.
For presentation, the first question is, current power is 25 megawatts, but which power you're considering to be like as a final project?
Okay. 25 is the next. The real power of the prototype is a bit over 30 megawatts, but this is not the difference. The commercial modules are expected to have 400 megawatt thermal. I say that because we are considering, like Chinese have done with the high temperature reactor, to use one turbine for 2 reactors. So I will not say 120 because we will use 2 reactors to fit 1 turbine. That is under consideration. So the thermal power will be about 400 megawatt. This is something like 120, something like that in a conventional PWR. This is related to the size of the pressure vessel. The limit is related to the size of the pressure vessel. We are considering for that not the larger pressure vessel that can be constructed in the world, because, for instance, the BWRs can make very heavy. Hitachi can make
6 meters.
but more than the problem is which is the weight that the foundation of our factory can handle. You can, if the foundation are designed for a given weight, you can't handle more than that. So, but it's related to conventional PWR's weight. But so, having this limit to not go beyond 400 or 500 tons, this fixes you the higher power you can get from the model. Please.
I have 3 questions. The first one is how the experience of Arusha helped to develop CAREM and like the environment and the supply chain in Argentina changed after the decision of designing in Argentina.
Well, in Argentina, we are few people. Argentina is, maybe the land is large, but we are not as much people in Italy. We're a bit more than Canada, but not too much. So we use all we have. People from Nuclear Electrica is the utility that has finished Atucha, is working also in CAREM. For instance, now they are finishing the building, and they have a lot of experience. We are, for us, related to operation and maintenance of nuclear power plants. And they could be the one who will operate. So this is strongly related to the suppliers. We are building capacities in Argentina, but we will not develop everything. As you can see, we buy the turbine from Germany, we buy the forges from Italy, we are buying components from America or even Europe, also valves from Italy for the balance plant.
Okay.
We are strongly developing because in Argentina we have for oil and gas a very important industry related to static components, vessels, heat exchangers, and a lot of engineering related to that. And one thing important is that for the pressure vessel, we have a company and we require to be N-stamp. N-stamp, what? This is Europe, but N-stamp is a requirement of the American ASME. For the rest of the components, we are applying the same design codes and the same way of dealing, but we are not requiring the stamp. We are applying our own controls and developing put the assurance way to certify that and to make the conciliation. Conciliation is a very important thing. You also, Ansaldo, do a lot of these kind of things when it's supplied to. Ansaldo is a supplier, for example, to embalse, for plants. Conciliation means that you do not require given supply to depend on all the nuclear standards, but you help him with the controls to get the target working with him. Why we do that? Our market yet is not so big to force a company to develop all these things that cost a lot of money. And what happens? If you don't sell more, after 3 years, you lose everything. So that no sense. What is important is to assure the quality. So as owner and designer, you need to help them. Or it's more work for you, but it's the cheapest way.
The second question that I had was there were some challenges at the start of the reactor, given the self-pressurization.
We have to solve the self-pressurization before getting the license for the revolver. So it's not related to the construction. It was related, all the things that I have to explain were necessary to convince the regulatory body to give us the permits. But when we start the construction, we are not having, let's say, an issue related to self-pressurization for the construction.
No. But for the operation, you are...
The operation is at nominal power, the operation is easier, but you need to have some care, and care means a special procedure during the startup. We need to have special procedures during the startup. Being the prototype, we have made the following decision. It seems that it will work properly, but we have added, let's say, a startup pressurizer. So we have external pressurizer specifically designed for the prototype to be sure that we can go and check everything. So this is something we have added in the prototype because we want to test that, but if something happens, we need to ensure that we will be able to start up the system. So this is a good question, but I will think that you must think it as a tool when you are developing a prototype for the price of the kind to be sure that you can get, but not be in love with this system, because if you don't need, you will not use it in commercial.
And the third question was if there were some other reasons besides the economic one to develop a non-heavy water reactor instead of like Atusha that is heavy water.
Yeah, okay. But this is related to the Argentinian system. And when I was, I don't know if I was born, but in the 60s, Argentina decided to go to nuclear and to use natural uranium. So at that time, they have analyzed gas graphite, cool and graphite moderated reactors and heavy water reactors. So the decision was made to build heavy water reactors to be sure that we can assure the supply of fuel because it was natural uranium. For Argentina, it was also important to be sure that we can get the fuel because you build a reactor and you need the fuel to operate it for decades, a long time. The business related to fuel is larger than the business related to the construction. in the early 80s, Argentina has developed granular enrichment as a facility, not as a commercial plant. Why? Well, I said that we have exported research reactor. Research reactor is but it's also used for radioisotope production. For Netherlands, they don't want to make research; they want to produce radioisotope. And they use enrichment. And if we are selling research reactor, we need to be sure that. So, in the 80s, I think I checked. In the 60s, Argentina think that to develop a region will be a long way. So we want to have natural uranium, and there were people like Canada or Germany that were offering, even the English people, and even the French with the graphite and gas. So in the 80s, the situation was different. Atucha 2 was started before uranium enrichment was achieved. But it was delayed for a very long time. But it's something important related to Atucha, that Atucha is really PWR, where you get out the rich fuel from inside, and you fill it with heavy water and natural uranium, and a kind of calandria inside to get pressure tubes, but they are not pressure, but flowing tubes. So all the technology related to both systems of Atucha plants are convoy type systems. So PWR. So there are a lot of things that happen. One thing that is also important is to produce heavy water, we have a plant, but it's a chemical plant, and with the time, it is always more expensive to keep them producing. So what happens 20 years ago may not be economically the same now. Last question?
I'd like to ask, let me say, which is the feeling on nuclear energy in Argentina, not only on nuclear energy, but also on CAREM 25.
Well, feeling. I understand. Well, I would try to be, let's say, it's a development, and you see that we are building a prototype because we feel that it's very difficult for someone to buy a first of all. Not because it will not work, just because the performance will be not the best. And if you are buying a plant, you want electricity, you don't want the delivery. So we are hoping to learn even of our mistakes. There are things that we already know that this will change it. It could be better. But it's important to go through all the way, because in the paper, most of the things works. But when you are trying to get it, probably they work, but the cost is different. So we hope that we could finish the development. It's a development yet, because we want to be sure that all works and to adjust the things. And we expect to be able to build in Argentina and also export in a moderate way. Moderate way means we will not fill the world with them, but we feel that we have enough space to get a part of the market. But in Argentina, we are also thinking more. We have an agreement with China to build The final contract is not signed because there are some financial, also the financial details are harder than the others. To build a 101 PWR. So it's also part of the answer. We are not only building that. We are going from naturally lining reactors to PWR type reactors as the normal way because the world changed, the supply has changed, so we need to adapt to the world. And of course, we are also working with research reactors. As has mentioned, we are doing the conceptual engineering for Netherlands. And this will be the first time we build a reactor in Europe. We have built in America, in Africa, in Oceania, but never in Europe.
Okay, thank you very much, Eladio. Let's go here to the seminar.